CRT filters make extensive use of GPUs by duplicating complex visual effects like scanlines, bloom, curvature, and pixel manipulation in real time at high resolutions. These effects attempt to recreate the nostalgic appearance of old CRT monitors that were once widely used before flat panel displays took over. CRT filters, often used in gaming and video editing, are designed to replicate certain characteristics of CRT displays, such as the unique glow, color reproduction, curved screen, and low resolution, making modern footage appear as though it was created on an outdated CRT screen. While these effects are aesthetically pleasing to some, they significantly increase the GPU load due to their demanding nature. The CRT filter effect tries to reproduce several features of old CRT screens, including scanlines, light effects, color bleed, and curvature. These effects simulate how light interacts with the screen and how electron beams work in CRT technology. This involves intricate algorithms and mathematical calculations that require a substantial amount of processing power. One of the main reasons these filters burden the GPU so much is that each frame of a game or video requires these effects to be applied in real time. The GPU must compute and display these effects dynamically for every frame to maintain smooth and accurate visuals. Creating scanlines, for example, requires the GPU to generate a grid of horizontal lines on the screen. And to achieve bloom and glow effects, the GPU must blend various color layers and adjust pixel brightness. Similarly, the curvature effect demands further computations to simulate the rounded screen of old CRT monitors. These effects require high pixel manipulation, especially at higher resolutions like 1080p, 1440p, or 4K, where millions of pixels need to be adjusted for the effects to appear correctly. Another contributing factor is real-time rendering. Since CRT filters are applied to every frame in gaming and video editing, the GPU has to continuously recalculate these effects at 30 or 60 frames per second. This real-time processing is intensive, as the GPU must ensure that the results are both accurate and smooth, putting additional strain on the system. Shaders, which are small programs that simulate CRT effects, add further complexity by manipulating textures, performing mathematical computations, and adjusting pixels. More advanced shaders require even more GPU power, and when paired with additional effects, this can push the GPU to its limits. The overall processing load on the GPU increases when these effects are combined with other performance-demanding effects such as motion blur or anti-aliasing. The GPU has to handle both the CRT effects and the background, foreground, textures, and image lighting. This combined load further increases the GPU's workload, requiring more resources to produce high-quality, seamless images. The main challenge with CRT filters is real-time rendering. These filters simulate the behavior of an entire display system in real time, requiring intricate calculations for effects like scanlines, pixel grid effects, bloom, and color bleed. The GPU needs to apply these effects dynamically as the image changes, making continuous recalculations necessary. The process of downscaling the resolution to replicate CRT displays, adjusting for curvature, and creating light effects like bloom and glow requires additional GPU resources to perform the necessary calculations for every frame. In conclusion, CRT filters are demanding on GPU power due to their complex, real-time effects that manipulate every pixel on the screen. These filters replicate the characteristics of old CRT screens, including scanlines, bloom, color bleed, and curvature. High-resolution rendering, real-time recalculations, and shader complexity all contribute to the substantial GPU load. To reduce GPU usage, users can adjust the filter settings, lower the resolution, or opt for performance-oriented CRT filters, which can help maintain the desired visual effects while improving system performance.